Alright, in this video we're going to continue our discussion about electronegativities since it's such a useful concept in all of chemistry, including organic chemistry all the way actually. So we would like to spend a few more minutes here to explain how is electronegativity applied in when we try to understand the chemistry or we try to understand the compound as well. So the atoms in the different elements on the periodic table, they are all seeking to become 8 valence electrons, and due to different number of valence electrons they already have, they show different electronegativity. So some of the elements tend to lose electrons, some elements tend to gain electrons. So when two elements, or actually when two atoms, they find what they're trying to find from each other, then they're gonna tend to do chemistry, or they tend to form bonds, so to form a compound. So here, what we want to say here is there are basically 3 types of chemical bonds here: ionic bond, polar covalent, and non-polar covalent. The different type of compounds essentially are due to that when you have 2 elements, they are different in electronegativity. So for example, when one atom has a high electronegativity, that means it wants to get more electrons. And when an atom has a lower electronegativity, that means it's a very good electron donor. So one electron, in general, one electron donor meets another electron taker, then they're gonna tend to form a compound. The electron will be transferred from the low electronegative one to the high electronegative one. Now when this happens, this will become an ionic compound. We've seen that in the case of sodium and chlorine, the electron transfer from one to the other, forming cation of sodium and anion of chlorine. So this is so-called ionic bond because the bond is a natural attractive force between the positive charge and negative charge. Now there are also cases that when 2 elements are essentially the same thing, okay, such as carbon and carbon, now they both want something, but they can't transfer electron from one to the other because they're not too much different. Okay, so they tend to share electrons. Sharing electrons meaning they're going to provide 1 valence electron from each atom and having a pair of electrons in between them. Okay, there's no ions, there's no charge. Okay, there's no one lose electron, there's nobody gain electron. They're just sharing electrons. So they're called non-polar covalent bond. Okay, there's another cases, okay, which is kind of sits between the ionic bond and non-polar covalent bond, which is when you have one atom, okay, has high electronegativity when the other atom has a low electronegativity, but they're not. The difference here, what we're trying to look at is the difference in electronegativity. It's not big enough for the donor completely donating 1 electron to the taker. Okay, so let's take a few actual examples to get a better understanding of how this works. Okay, so for instance, here's the atomic diagram of lithium and fluorine. Okay, now they have very big electron negativity difference. Okay, so the lithium has 1 valence electron here, and the fluorine is missing 1 valence electron, which has 7 already. Okay, it's missing 1 from 8. So the fluorine is going to take this electron completely away from lithium. All right, so this results into lithium with plus symbol, that's a cation. This is a fluorine with negative symbol. Okay, the total number of electrons is not changed, but just transfer from one neutral atom to another neutral atom. So this results into cation and anion, 2 ions. So this is an ionic compound. Okay, this usually happens between most of the time. Okay, if you see a metal and a non-metal, so this is usually what happens. Okay, now when you have fluorine, which is the most electronegative one, okay, which in other word is the best electron taker or is the most aggressive electron taker, whatever you want to name it. Okay, what if fluorine meets another fluorine? Okay, so they two are identical. They both are electron taker. Okay, but they can't take electron from someone who is just as aggressive as itself. But they both are desperately need 1 more electron. So they have to come sit down and then come up with a plan like this. So they're going to share a pair of electrons between them. So there's nobody gain electron, nobody lose electron, okay? Even though they both are pretty aggressive electron taker, but they're going to share a pair of electrons, usually represented by a dashed line between two symbols of the elements. Now, by sharing this electron, okay, the fluorine on the left will make it look like, even though it doesn't really, okay, make it look like there are 8 electrons around it. Okay, so basically what it's trying to make it seem to be like is this. Excuse me. And on the right hand side, the fluorine also, by sharing one more electron, will make it look like this. So the 2 electrons in between them becomes essential to keep both fluorine atoms satisfying by the octave rule, with 8 electrons. Since they both have equal power to pull these 2 electrons towards each other, okay? So you can imagine there are 2 equal forces pulling these 2 electrons. So the bond between them are covalent bond, but also are pure covalent bond. Nobody gains, nobody loses, okay? This is not going to be the case when we look at the next example, okay? The next example is going to be so-called a polar covalent bond. So by name, you can see we're still talking about covalent bond, but this covalent bond is not balanced, okay, between 2 atoms. The example we're seeing here is one hydrogen atom and fluorine atom. Both are non-metal elements. Okay, so this is polar covalent bond usually happens between 2 non-metal elements. Okay, fluorine obviously has a higher electronegativity than hydrogen, so it's trying to pull this electron to fluorine from hydrogen, but it's the difference between hydrogen and fluorine is not that huge. It's not like sodium and fluorine. Okay, so what's going to happen is they're going to still end up by sharing these 2 electrons. So the hydrogen, like we already said before, okay, it only needs 2 electrons around the nucleus, whereas fluorine also gain, well, not regain, will look like has had 8 electrons around it. But the 2 electrons shared here, okay, which is also represented by a dashed line between hydrogen and fluorine, it's going to be closer pulled towards the nucleus of the fluorine, because we already said that fluorine has stronger or higher electronegativity than hydrogen. Okay, so it will look like these 2 electrons, the shared 2 electrons, are closer to the fluorine nucleus. So we say, okay, this is a covalent bond. Okay, 2 electrons are shared, but they're not equally shared. So that's why we call it polar covalent bond. Polar means it's been orientated towards a certain direction. Okay, so these 2 electrons are more towards oriented to the fluorine atom or fluorine nucleus, a little bit further away from hydrogen nucleus. Okay, this result into a unbalanced sharing, which is essential. As a matter of fact, okay, organic chemistry, most of the bonds are polar covalent bound. Okay, so we're talking about millions of compounds. Okay, most of the compounds, or pretty much all of the compounds, are formed by these 3 type of bonds. Okay, ionic bond, covalent bond, and pure polar covalent bond and non-polar covalent bond. Okay,